In question 1, a disk of radius r and mass m rotates without friction around a vertical axis with an initial angular speed of omega naught. A second disk of radius 1/2 r and mass 2m that is aligned with the axis of the first disk is dropped onto the first disk and begins to rotate with it in an inelastic collision. Part A asks how the angular momentum of the two-disk system compares to the angular momentum of the first disk before the collision. Since there are no external torques acting on the system, the angular momentum of the system is conserved before and after the collision. Part B asks how the final angular speed of the two-disk system, omega final, compares to the initial angular speed, omega naught. It gives us 5 choices, and the answer is that 1/2 omega naught is less than omega final, which is less than omega naught. Since the initial angular momentum is equal to the final angular momentum, the initial momentum times the initial speed is equal to the final momentum times the final speed. Lastly, if you solve for the final angular speed, you get that it equals the initial momentum times the initial speed, all divided by the final momentum. It is the second answer because if you think about it conceptually, the final angular speed isn't much smaller than the initial angular speed because the two-disk system has more mass than the first disk before the collision. But the mass is more centralized after the collision, so the angular speed of the system decreases after the collision because it is harder to keep it spinning than just the original disk itself. Lastly, Part D asks what is one change you would make to this experiment to increase the value of the final angular speed. As seen in Part C, a more centralized mass is harder to keep going, so it slows down. To increase the angular speed, you could distribute the mass differently by adding a larger ring with the mass spread out around the edges, because it would have a higher angular momentum and also speed. Question 2 says light bulbs of fixed resistance 3 ohms and 6 ohms, a 9-volt battery, and a switch S are connected as shown in the diagram. The switch S is closed. So Part A asks us to calculate the current in bulb A. This is a parallel circuit, so voltage is the same across the branches, but the current is split among the branches depending on the resistors. The inverse of the resistance of the path equals the sum of the inverses of the resistors in the path. So Rp equals 2 ohms. We then add 3 ohms from the path containing bulb C to get the total of the resistances. So RT equals 5 ohms. We then find the current by dividing the voltage by the resistance. So the current equals 9 volts over 5 ohms. So the current is 1.8 amps. Part B then asks us to find out which light bulb is the brightest. To see which light bulb is the brightest, we have to calculate the power of each bulb by squaring the current and multiplying that by the resistance for each bulb. So we use the equation P equals I squared times R. So for bulb A, the current is 1.8 amps and the resistance is 3 ohms. So P 0.8 amps squared times 3 ohms. So we get 9.7 watts. Now we do the same thing for the respective values of bulbs B and C, except that the currents are divided by 3, and also the 1.8 amps for bulb C is divided by 2 because it is in parallel instead of series. So for bulb B, we use 1.8 amps squared divided by 3, that's all squared, times 6 ohms equals 2.2 watts. And for bulb C, we use 2 times 1.8 amps over 3, that is all squared, times 3 ohms to get 4.3 watts. The power of bulb A is 9.7 watts, B is 2.2, C is 4.3, so bulb A is therefore the brightest. Part C says that switch S is then opened. We have to indicate whether the brightness of each bulb increases, decreases, or stays the same when the switch is opened. So for bulb A, the brightness would decrease because brightness is dependent on power. For bulb A, the resistance would increase because the electrons cannot travel on these two paths. They are just restricted to one. The increase in resistance means that the current would decrease so that the power would also decrease. Bulb B, on the other hand, would increase in brightness. The current would increase because energy to bulb C, the other parallel circuit, is shut off when the switch opens. The electrons would now have only one path to travel on, so the resistance increases, and therefore the current increases. The current of bulb B increases, causing the power to increase as well. Bulb C would decrease in brightness because it would be shut off when the circuit is broken. The current becomes 0 when the switch is opened. In question 3, a ball of mass m is attached to a string of length r and has negligible mass. The ball moves clockwise in a vertical circle as shown. When the ball is at point P, the string is horizontal. Point Q is at the bottom of the circle, and point Z is at the top of the circle. Air resistance is negligible. Express all algebraic answers in terms of the given concepts and fundamental concepts. Part A says that on the figure below to draw and label all the forces exerted on the ball when it is at points P and point Q. The forces of gravity and tension act on the ball in both places when the ball is at those points. The force of gravity always points down, while the force of tension points to the center of the circular path that the ball is traveling. Part B asks us to derive an equation for the minimum velocity, the minimum speed the ball can have at point Z without leaving the circular path. So we start with the net force is equal to the mass times the force of gravity. We also use the equation mg is equal to the mass times the minimum velocity squared over the radius. By simplifying, the big m's cancel, and we take the square root, and then we end up with the minimum velocity is equal to the square root of the radius times the force of gravity. Part C says the maximum tension of the string can have without breaking is T subscript max. Derive an equation for V subscript max, the maximum speed the ball can have at point Q without breaking the string. So from the equation from part B, we find that the mass times the maximum velocity squared over the radius r is equal to T max minus the mass times the force of gravity. After simplifying this to solve for the maximum velocity, we get the velocity max is equal to the square root of r over m times T max minus mass times the force of gravity. And that is our answer for part C. Part D says that suppose the string breaks at the instant the ball is at point P. Describe the motion of the ball immediately after the spring breaks. So it will travel straight up, like this, because there will no longer be a centripetal force acting on the ball, and it will want to travel in a straight line, as objects in motion naturally want to do according to Newton's laws of motion.